This video presents some of the rules for drawing free body diagrams, but doesn't go through them in a particularly formal order. Instead, I'm going through what are in different textbooks over a period of 75 years to sort of compare and contrast what people thought were important at various times. Every book has got something in it that's important to know about. Each book emphasizes something that at that particular time was thought to be particularly important to pay attention to when you were learning this subject. Usually a result of discovering that students didn't do something right, so they emphasize that in that book, and then leave something out of that book that someone else later on has to emphasize. And so in the process of putting together how I teach this material, I've drawn from many things, my own experiences teaching the class and also various books that I've used at the time. First book, though, is one I never used. My father used it when he learned physics in 1946. The book was first published 75 years ago and was in its 23rd printing as hundreds of thousands of people who had never thought about going to college before entered college under the GI Bill. Interestingly, one of the authors of this book is an electrical engineer, not a physicist. You don't see that much anymore, but it has a very practical bent to it. I'm going to dictate a few of these things so you can hear my emphasis on the words. The authors write that experience has shown that much difficulty can be avoided by following a definite procedure. I'm going to say full stop, period, end of story. Much difficulty will be avoided by following a definite procedure. They continue by saying, yes, when you're thoroughly familiar with the subject, you can probably cut corners here or there. But my view is that the more familiar you are with the subject, the more experience you have, the less likely you are to cut corners here or there because you know that cutting those corners results in mistakes that make bridges fall down. Once you're past that, the fundamental thing is that you select one body for consideration. This might be the body being accelerated, but it might just be one of several bodies that are interacting in a particular problem. Now the long paragraph. It's about the most important thing, which is drawing what's called a free body diagram. It's a force diagram. It's separate from the space diagram. So I want to say something about this first sentence. You're always going to have two separate drawings. One of them is a drawing, a picture that shows the conditions of the problem. On that picture, you can sort out what are the forces acting, maybe even list the forces that are acting, sketch some of the important details of the problem, the details that you're going to use when you build the free body diagram. The free body diagram is a separate drawing that's more of a cartoon. It's really maybe even a doodle where all of those details are reduced to just a single point for the body and arrows showing the forces. Period. That's all. You've got to be very careful, they emphasize this, to not leave anything out that matters and not include anything that doesn't belong. Either of those mistakes are fatal. Now there's one weakness of this description. They never mention the coordinate system choice. In the next set of steps, they say, yes, you need to find the resultant or unbalanced force. Implicit in this is that you have a coordinate system that allows you to write those forces in terms of their components and solve the vector equations. But they don't emphasize that point. That's a point that we emphasize a lot more today. The equations that they mention in here are, of course, just A equals F over M or net force equals MA. Those are given elsewhere in the book. Now, my second example comes from a textbook which was the first book I taught out of. I didn't learn physics from this book, although I learned a great deal when I taught out of it. It's called Halliday and Resnick. It was first actually developed out of a book written in 1960. In 1962, they wrote a second volume that became part 2 of the 1966 edition. Then they actually rewrote and combined those into a book that was then used for the next at least 11, 12, 13 years before a new edition was produced. I taught out of the 14th printing of that book. Here's what they have to say. They start off a little weak. It'll be helpful to write down some procedures for solving problems. No. It's necessary to have some procedures for solving problems. You might not follow exactly their procedures, but you must have a procedure. After that, it gets good. Newton's second law says that the vector sum of all forces acting on a body is equal to its mass times its acceleration. That's telling you you must find that body, find the forces on that body, and then use that information to solve for the acceleration. That's the key idea of a free body problem. A free body diagram is to isolate that body and attack that part of the problem. They also have a very strong emphasis on the key point of the dangers inherent in not being clear about what body you've chosen, and in particular, what forces act on it. They don't emphasize that as much as they could, but they do in the very next step. I'll add that Wilson has a separate chapter on the multi-body problems that is devoted to splitting things apart. Now the thing that I really like about this book, he says, after you found the body, what's acting on it? What's in the environment? They even list what those things are. Inclined planes, surfaces, springs, cords, ropes, cables, whatever. The earth that's producing gravity, acting on the object. This is actually really important. In your picture, in your first diagram, you can list what those forces are. You should have them sketched on that picture so you know everything that's involved in that particular problem. And in fact, use things like the inclined plane surfaces to choose the suitable coordinate system. Notice that their third step now spells out very clearly something that was left out of the previous book, and that is the importance of choosing a suitable inertial, that meaning Newtonian, reference frame coordinate system. Put the coordinate axes to simplify our task. That usually means something very specific, although they didn't spell that out in this book. They are telling you it's important to do that. Put the origin in a useful place, orient the axes in a way that will not make the problem harder, but rather make it easier. I want to emphasize from our textbook's point of view, this is now part of the interpret step rather than the develop step. That is, while you're looking at the picture, the diagram of what's going on in this problem, you're interpreting what are the forces and what coordinate system to use. Now I repeat step 3 here just so you can see how it blends smoothly onto step 4. After you've got your coordinate system drawn, then you make a separate diagram of the body, the free body diagram. So you show the reference frame in that separate diagram. That's crucial. Have your reference frame in that second diagram, put the dot at the center of that reference frame, and then show all of the forces acting on the body. This is the develop step. The last part, write down the equations, blah, 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 blah. That's like, okay, yeah, and then you solve Newton's laws. They don't say a whole lot about that, but it's also really important to pay attention to that. Okay, the third example is from a book that I used for quite a few years here at TCC. It's a successor to a book that was one of the second generation books published around. This one was published in 1976. There were a couple other books around that same time. First generation books include things like Sears, Zemansky, Young, and Friedman that was written about the same time as Halliday and Resnick. This particular edition has a co-author, Gene Mosca, along with Paul Tipler. We have it in the Learning Commons, by the way. Notice that they start off with a very nice statement, draw a neat diagram, that is the picture that has all the features of the problem. Okay? You might have that picture in an exam problem, you might have that picture in the textbook problem, but if it's not there, you need to draw it yourself so you have that picture for reference that shows all of the features, including surfaces and forces and other bodies. Then you isolate one of the objects of interest. If there's more than one object, you might draw circles around the separate ones in order to identify each of them in turn so you can draw a free body diagram of each one of them in turn. Now, they say identify all the forces. They don't go into as much detail as Halliday and Resnick did about that step. It is important to find all of the forces acting on the body and identify them clearly in your problem. They elaborate very nicely, however, on the issue of choosing a coordinate system, including a key detail. If the direction of the motion is known, like for an object sliding along a surface, choose one of your coordinate axes parallel to that motion. For example, parallel to the surface. This is an important detail. If the thing might fall straight down because of gravity, because there is no surface in the way, then you use the standard system where one of those coordinate axes is vertical. Then, this is pretty straightforward. vector sum of the forces equals ma. If there's more than one body, third law, and so on. This is all pretty straightforward. But I wanted to point out step 6. This is one of the early appearances of the assess step that is really emphasized really hard in all of the modern books, all of the books that have, say, been written in the last decade or so. Check to see whether your results have the correct units. Are they plausible? Sometimes you can plug in large or small numbers to see whether or not it makes sense. But assess your answer to see whether it's got the right units, the right sig figs, and it's not ridiculous. Okay, the book we're using, Richard Wolfson's second edition. Actually, I started with the first edition in 2007. The pictures here are all from that first edition, but the page numbers and references are to the current book. The interpret step is very much like you see all the way back in Halliday and Resnick. Identify the object of interest and all the individual interaction forces on it. But I'd refer you back to that Halliday and Resnick statement where you want to spell out all of those things, including surfaces and cables and so on, to identify those. Now, what I don't like is that the coordinate system is chosen after you draw the free body diagram. You can do this. If you're really good, in fact, you can do it this way, because once you got the diagram drawn with all of the arrows for all of the forces, you can write the law in components using any coordinate system you want, even ones that are bad coordinate systems from the standpoint of convenience. It will work. It just won't work very well. However, it is more efficient if you can choose that coordinate system at the interpret level so that you're drawing your free body diagram in that particular coordinate system from the beginning, and in fact, you can then write the components, which is down under the evaluate step here. Write the components of Newton's law in the coordinate system you chose. You can do that while you're drawing the free body diagram. You can write the components down as part of the develop step before you actually get down to the evaluate computing step. A very nice thing in Wolfson is he pulls out the drawing free body diagram step as an actual separate tactic. Identify the object of interest, have the object as a dot, draw the vectors. The only thing I would add to that is it's really convenient to have those vectors on the diagram, the picture that you have beforehand, so that when you draw the free body diagram, you decompose the force into components and draw the components in the free body diagram on the coordinate system you're planning to use. That's a much more efficient, faster process than the one that is typically described. Okay, I want to give one quick example. You've seen this in class, you've seen this in the lab, you've done it as a homework problem, you've done it in a pre-lab problem. Key step to doing an inclined plane problem like in our first lab is using the right coordinate system. The box is on an incline, it is going to accelerate parallel to the incline, it is not going to move into the incline. So a natural coordinate system is one parallel to that acceleration vector, that is parallel to the surface of the table. That also automatically means that the contact force between the surface and the body, which is normal, that is perpendicular to that surface, will be also along a coordinate axis. That is a particularly useful thing. Gravity is not in a convenient direction, but it is easier to decompose gravity into its two components than it is to do the opposite, that is, turn the normal force into its components. Because when you break gravity in its two components, it becomes clear that one part of gravity is balanced by the normal force, by the perpendicular contact force, and the other component of gravity is unbalanced and causes acceleration. If you strip away all of the details and leave only the arrows I show in color there, you have a very nice, clear little cartoon of the problem that shows you what the free body diagram tells you. It tells you that the normal, that is perpendicular contact force, must be opposite the mg cos theta force from gravity, and that the mg sine theta force component from gravity is unbalanced, so that g sine theta becomes the acceleration of this mass. Okay, so you need to practice so that whatever procedure you develop becomes second nature. So you automatically get everything you need into a free body diagram. Don't leave anything out of the free body diagram. Don't include anything extra in the free body diagram. It's also, I think, important to emphasize that if you come out of this class only knowing 50, 60% of this, that's okay. It's the head start you need when you get to your next class. And I'm just going to close with a appropriate reference to the various media I've used and the scans I've used, all as fair use in the teaching of this class.